So we're really nice position now to start answering the first question, the question of finding slopes. That's why today's a really nice day. We finished chapter 1, the intellectual backbone behind everything that we're going to do, the epsilon delta definition. Okay, talk is cheap. Let's find slopes. So we'll start off with the levels, what I call level 0, the easiest slopes in the world. These slopes should be no match for our skills by now. You can go something like this on them. You can go, alright, so the slope is different at every part of this, every portion of this graph. You could say, hey, you know what, I'm going to take it by portions. Here, for example, I'll find the slope. I'll just find rise. Oh, from 6 to 0, that's 6. I'll find the run, that's 2. So the slope is, for that portion, the slope is equal to 6 over 2. And I get something more meaningful if I add the labels here. 6 miles over 2 hours. So 3 miles per hour. So I'm getting the interpretation of the slope is that the average velocity here from 0 to 2 hours was 3 miles per hour. So we were traveling. This is the amount of miles traveled. This is the time. The slope tells you how fast you were going the first 2 hours, 3 miles per hour. And then you do this next one. The slope there is really easy. It's 0. It's flat. There's no rise and there's some run. So you are not traveling very fast there. 0 miles per hour. And then you can go on and you figure it out here, and you see start to get comfortable with slopes. Rise over run from 6 to 20. That would be 14 miles over from 4 to 5, 1 hour. So it would be 14 miles per hour. So you picked it up there a lot faster, and then here you were flat again, miles per hour. That's the kind of stuff we've got to do. We got to be good at finding slopes and interpreting them. But of course, this was way too easy because the lines were really straight. What we really want to do is we want to change it up a little bit. Instead of being straight like this, we want to see what would happen if it's curvy. It's exactly almost identical. The same sort of stuff was happening. You were going fast. You were going kind of flat for a couple hours. You were standing still. Then you picked it up a lot, going at approximately 14 miles an hour. Then you were flat again. It's almost identical, but the difference is totally a world worth of difference. It's just so different because these lines are curvy, and never before, if you're taking this class as a standard student, you never before had ever found the slope of a curvy line. In fact, we don't even define it. Usually, we usually only define slopes for lines, not for curves. But here we are. We're going to do something more or less like that. We're going to define the slopes for curves. And to do that, we start off by defining a secant slope. Now, a secant slope is one that touches a curve at a couple different spots. You see, this one touches a curve there, and it touches a curve there, and you make the line between the 2 points, a line between 2 points in the curve. Here, line between 2 points on the curve. That right there, that's a fancy name for that. It's called the secant slope. The slope of that line is called the secant slope. But of course, this is rather easy. Why? Because you've got 2 points here. You got 10 and 20. So this point is 10 and 20. This one's 4 and 6. So it's child's play. We can easily find that slope from 4 to 10. I'm looking at these labels here from 4 to 10, or look at the x values here from 4 to 10. From 4 to 10, that's 6, and then you look at the y's, or either you look at the y coordinates here, or you look at the y coordinates here. Same thing, from 20 to 6 is 14, and so you get that the slope is equal to 14 over 6. Now, sometimes I may stop labeling these things. I hope I've sold you on the idea that the labels are incredibly important. Every time you slap meaningful labels on this, you get a meaningful label for the slope. But I'm going to shift my attention to just finding slopes, and I hope that I've sold you on the idea that the labels are super important. In fact, that's why the whole question was important. Anyways, secant slopes still are no match for our skills. Any old chump can find secant slope. Probably even a dolphin could find a secant slope. It's that easy. But humans can do so much more than finding secant slope. Really, what we want to do is not so much a secant slope, but we want to find a tangent slope. Now, tangent slopes are different than secant slopes. Here are some of the differences. At that point right there, they look like they barely touch it once. They touch They touch at one point, at least in this case. And not only that, but that's not the whole definition. The other part of the definition is that at this point it has to really approximate the lines so much that they almost look indistinguishable. If you were to zoom in and zoom in and zoom in and zoom in, an incredible amount of time of zooming in, it would look almost indistinguishable. When that happens, and it barely touches at a point, or maybe it touches at more than one point, that's not as important as the fact that it's really approximating that. With a straight line, you're approximating a curvy one. When that happens, that's what we call a tangent slope. So here's what I was trying to say. If you zoom in there an incredible amount of time, zooming in from far into it, it looks almost identical. The curvy line and the tangent line, this is called the tangent line, they look indistinguishable. That's what we call, geometrically, that's what we call a tangent slope. Not all curves have one at all points, but sometimes they do. And this is really not a new concept for us. If you think about how pervasive this concept is, let me give you an example. You're probably walking on an example like that right now, or you're sitting on one. Salute. Oh man, you guys gotta turn your phones off. So I was saying that this concept is really pervasive. The idea of approximating a curvy figure with a straight one. Think about where you're sitting right now. Look at the floor. Does the floor look flat to you? It probably does look flat. But that's because the Earth is so huge. It's got a radius of approximately 4,000 miles. If you're just standing here and you look at the ground, it really looks flat. That's because you're zoomed in so much that, when it looks indistinguishable. And so this idea of approximating a curvy curvy line with a straight one is not that new to us. In fact, for thousands of years, people thought the world was flat because everywhere you go and you look around, it looks flat. That's because you're zoomed in an incredible amount of time. In fact, when people make buildings, when people design plans, often they pretend that the world is flat. And that's because locally it is. Not every single little spot, it more or less looks flat. Okay, save your letters. I know it's not really flat, but it looks flat. Alright, so that's, if you can do that geometrically, that's what we call a tangent line. Now, the interpretation, of course, on your miles per hour would be that at that point right there, if you were to look at that slope, suppose that slope says 5 miles per hour. That's exactly what the speedometer would look like if you were driving and you looked at the speedometer at that point, say at 1.75 hours into it. The speedometer, wherever it marked, say marked 5 miles per hour, that would be exactly the slope here. That's the interpretation. And of course, this is just one little tiny piece of it. The interpretation is huge. The moment you start labeling these things differently, the moment you start giving them different labels, oh, it's a world of possibilities. So often this is called the instantaneous rate of change. And most textbooks will tell you, well, it's the instantaneous rate of change of this function compared to time, but or compared to this. But really, because these things could be so different, the implications are huge. All right. Anyway, so that enough of that. That's what it means geometrically. It's the best fitting line, sort of, the best linear approximation. Not sort of. It is the best linear approximation. If such a thing exists. And that's the interpretation. It's the instantaneous rate of change of y compared to x, as opposed to the average one, which is a secant. This is average rate of change. This is instantaneous rate of change. This over here would be the average velocity from 4th hour to the 10th hour. This over here would be the exact velocity at 1.75 hours miles, 1.5 or 1.75 hours into it. All right, now enough of that. What we want to do now is focus all our attention, the remaining of the rest of today, in fact, the rest of the next week or couple weeks or maybe next month. We want to do nothing but become incredibly good at computing tangent slopes. That's the name of the game, computing tangent slopes. Because after all, this is a much better challenge. These other ones, a high school kid can do it. Your PE coach can probably teach you how to do that. Any old chump can do those. This is a much more interesting problem, so that's what we're going to focus our attention on. And what I want to try to sell you on today is the fact that it's not that hard. Well, the idea is incredibly brilliant and it's incredibly simple, but of course most ideas like that are hard to come by until somebody gets them, and then they look so incredibly simple. Just to make the analogy, it is roughly this simple. And I want to make this analogy just because I want to expose the simplicity and the brilliance in the idea. How do you turn milk into chocolate milk? Dun, 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 dun. Think. How would you do that? Well, it's so easy. All you do is add chocolate and it turns the milk into chocolate milk. That idea is so simple and so brilliant. Well, this one's not brilliant, but it's so simple. The idea of computing tangent slopes is that simple, but 1,000 times more brilliant. And the relevant question will be, okay, so if you've got a secant slope, we need one brilliant idea so that we can turn that secant slope into a tangent slope. How do you turn a secant slope into a tangent slope? It's almost as simple as how do you turn milk into chocolate milk, except it's 1,000 times more brilliant. How do you turn a secant slope into a tangent slope? If we can do that today, we will call it a success. And if we can become super good at it, we'll be really successful. That's the idea. Okay? How do you turn a secant slope into a tangent slope? Well, let me tell you. Let me count the ways. What we do is we first compute the secant slope. And let me see if we can compute the secant slope. The secant slope, you would make a little mark there and you would observe the x's and the y's here. And you would say, okay, the secant slope, I'm going to use SS for secant slope, would be the rise over run. The rise would be from f of x, that's this point, to f of 2, right here. So it would be that minus f of 2. And then the run would be how much you run in the x's, over here in the x's. So it would be x minus 2. That would be right there, that's called the secant slope. And of course the question is, how do you turn that secant slope into a tangent slope? And the answer is brilliant. All you do is you take your x here. Let me see, where am I? Here's the secant slope, super famous. You see it? Now what you do is you let's see if we can ungroup these. Ungroup. I'm going to move stuff around. So here's the brilliant idea. It's so simple and yet brilliant. You take the x and you move it closer here. What would happen if you move that closer? Instead of being over here, you'd have to move it closer to here. And the minute you move it closer to there, okay, now your line has to change. Now it goes like this. And now it's actually closer to the tangent slope. And then what would happen if you were to, I'm going to zoom you in there, okay, because this is really important. Look at that. Well, right. Let me see if you're focused here. No. Alright, we'll just have to live with that. What would happen if you move the point closer and closer and closer? Well, this line would have to move closer and closer and closer so that it keeps up with the points. And what would happen if I move it really close? Well, you got to move this point really close, and then it would be more or less like that. And then what would happen if I really move it close? Well, you see what's happening. That's exactly the key. The key to how do you turn a secant slope. Now we got to zoom out. That's exactly the key to how do you turn a secant slope into a tangent slope. Well, it's easy. You move the x point here closer and closer and closer and closer. You move the x closer and closer and closer and closer to the 2, and that moves the line closer and closer and closer to a tangent line. Instead of becoming a secant line, it becomes a tangent line. That right there, that's the key. It's so beautifully simple, yet it's so profound. This is exactly one brilliant idea for the ages. The idea of turning a secant slope into a tangent slope. And you know, summarize for you. You start off just with a simple secant slope, and then what you do is you slap a limit on both sides. You slap a limit on both sides and move the x closer and closer and closer to 2. And that, my friends, that has the effect of turning it into a tangent slope. I'll put it up here so you can see it. This is incredibly important. That turns a tangent slope at x equals 2 is defined to be the limit as x goes to 2 of f of x is equal to, or f(x) minus f of 2 over x minus 2. That idea is exactly what gets the job done. It's as simple as adding chocolate to chocolate milk to turn it into adding chocolate to milk to turn it into chocolate milk. That's how simple it is. All you do is slap a limit on both sides and you're good. Here it is. Let's try it on an actual function. So we're trying it with f of x equals x squared. Because we actually want to get a numerical computation. I think we've laid down enough ideas to actually start with a real example. So this is what we do. This is the brilliant idea. This is how we turn a secant slope into a tangent slope. That's what I'm going to explain right now. So you start off with a standard, function, and you pick a couple points. You pick 2. We want to find the tangent slope at 2. So you pick 2 and you pick some other x that's slightly off of 2, whatever, and you mark the point where it intersects, and then you mark the y. That would be f of x. This would be f of 2. This would be 2. And here you compute the secant slope. The secant slope, I'm going to use SS for secant slope. The secant slope would become the difference of y's over difference of x's. So I look at the y values, f of x minus f of 2. So that would be f of x minus f of 2. Then I look at the difference of x's, x minus 2. And that's my secant slope. Well, any little chump can figure that out. But here's the brilliant part. The brilliant part is when you take... We don't want the secant slope. We want to get from the secant slope to the tangent slope. So what are we going to do? Here's the brilliant idea. The brilliant idea is to move the x down. Move the x closer. I'm going to drop these green ones. Move the x closer to 2. And what happens when you move the x closer to 2? Well, then the secant slope would be slightly different. It would be more or less like this, right? It would have to go through those points. And you see, every little movement, such as that one, changes the secant slope into something closer and closer to the tangent slope. What happens if I move it even closer there? Well, I have to move this point over closer there. That was unintentional. Let's get rid of this one. I'm so fast. Okay, so then that would move the line over this way now. You see? Every single time you move the point closer and closer and closer to 2, your line is your secant line is being transformed. It's being transformed from a little low-life secant line into a tangent line. That's the transformation that's occurring. It's becoming from secant line to a tangent line. The closer and closer and closer I get to it, the closer and closer it becomes the actual tangent line. And that, my friends, that's a secret. The secret to changing from the secant line to the tangent line is, of course, to slap a limit. This is the secret. To slap a limit as x goes to 2. That's the secret right there. That's what will make out of a secant slope. It will turn into a tangent slope. It's like turning milk into chocolate milk. This is the secret ingredient. And the first part always starts off the same. The secant slope is more or less like that. And of course, here it is. This the idea that turns it is this idea right here, slapping a limit on both sides. Slapping a limit on both sides, the limit of the secant slope will be the tangent slope. So you can say this would be the tangent slope. And you can say at x equals 2 would be equal to the limit as x goes to 2 of f of x minus f of 2 all over x minus 2. Now this is so important that it will become our definition. We'll have 2 definitions of tangent slopes. This will become one of them. It's my favorite one, and that is worthy enough of being boxed. I think we should box that and rack it up as one of the most important ideas that we're learning for a long time. The tangent slope at x equals 2 is equal to the limit as x goes to 2 of f of x minus f of 2 all over x minus 2. That's the transformation. That's how you get a tangent slope out of the secant slope. Okay, now enough said. Let's actually do it, right? Talk is cheap. We laid out an actual function. We've got an actual number. Let's actually find the tangent slope at 2. So we proceed here. The secant slope, I'm going to go with green. The secant slope is equal to f of x. Remember, for this function, I don't know if you can see it or not. Here's a function. The secant slope is equal to f of x, which would be x squared, minus f of 2, which would be 2 squared, all over x minus 2. So the secant slope is equal to x squared minus 4 all over x minus 2. And here's the secret. The secret to turn it into a tangent slope is slap a limit on both sides as x goes to 2. The limit as x goes to 2, and that changes it into a tangent slope. Tangent slope at x equals 2 would be the limit as x goes to 2 of x squared minus 4 all over x minus 2. That has changed the question into just a limit question, and for that we should be experts at it because we've done so many limits in the last chapter. We've got our 4 limit methods: the plug-in method, the rewrite, the engineers, the graphing method, etc., etc. You try the plug-in method and you get 0 over 0, so you try a little rewrite. You try a little rewrite, and that would give you x minus 2 times x plus 2 all over x minus 2, and that cancels, and so you get x plus 2. You do the plug-in method and you get 4. Voila! We found our first tangent slope, which means that if you were to go back to our graph here and you were to find the well, this is obviously not drawn to scale, but if you were to find the slope of that line, the slope would be 4, exactly 4. So maybe you would write 8, you'd run 2. The slope is equal to 4. I know it's not drawn to scale, but just let that slide. If I was to draw it to scale, it'd be really, really steep, and the slope would be exactly 4. The slope is 4, as computed here by our incredibly brilliant idea of slapping a limit on both sides as x goes to 2, turn a secant slope into a tangent slope. And you can do this all day long. This is the secret. You can apply it to all the functions. They will all start off this way. Maybe the difference would be at the 2 if you wanted to find the slope at a different place. And maybe the function would be different if it was a different function. But the concept would remain the same. Just for fun, let's try it at 3. How would you find the tangent slope at 3? Well, you would still start off with the secant slope. So, okay, the secant slope is equal to f of 3. See, I did this one a little bit different because by the interpretation I had put x on the other side just to see if that works. And so I got f of 3 here, f of x here. So the difference is the secant slope would be f of 3 minus f of x all over 3 minus x. Based on where I place the x, it would work either way. This is a little atypical, but I'm not afraid to be atypical, as you probably already noticed. That should be good enough for a secant slope. Now, how do you turn it into a tangent slope? You slap a limit on both sides. Then this time, I want the limit as x moves closer and closer and closer to 3. So I'll take the limit as x goes to 3, x goes to 3. And that would give you the limit. Now, first of all, on the left-hand side, that would turn into a tangent slope. The tangent slope at 3 would be equal to the limit as x goes to 3 of... let's erase this one. Of 3 squared minus x squared all over 3 minus x, which would be equal to the limit as x goes to 3 of 9 minus x squared all over 3 minus x. You would try the plug-in method, you would get 0 over 0. So you try a little rewrite, and you would get the limit as x goes to 3 of 3 minus x, 3 plus x all over 3 minus x, and you would cancel these. Just a little simplification here, that's the rewrite. And that would give you plug-in method, that gives you a total of 6. See why they pay me? You see why they pay me insane amounts of money? That's telling you that if you were to find the tangent slope here, right here, guess what that slope would be? It's not a guess, it is exactly 6. Brought to you by the beautiful, brilliant idea, slapping a limit on both sides. The deep ideas behind limits, the epsilon deltas. It's perfection. Perfection in thought. So nice. But wait, there's more. You think that's all we can do is find the limit at 2 or at 3? No, we could find the limit for any point on this curve. We could always, all day long and all night long, we could do this so easily. All you do is find the secant slope and then move the x closer to wherever you want to find the tangent slope at. Let's do it one more time. Let's do it on the negative side. Suppose you wanted to find this tangent slope at -4. You think that's going to stop us? No. You first find the secant slope. Secant slope would be, I'll take the top minus the bottom, f of x minus f of -4 all over x minus -4. Okay? As long as you keep them the same, the f of x over x, the -4 over 4, you're good to go. And then you want to turn that secant slope. You want to turn that secant slope into. I'm not sure if you. This is important because that's where we need to plug it into that function. It would be different if this function was different. If it wasn't a parabola, the next step would be different. But this step is always the same. You slap a limit on both sides. Limit on both sides. And this time I want to go to -4. X goes to -4, and that turns the secant slope into a tangent slope at x equals -4, and that is equal to the limit as x goes to -4 of f of x minus f of -4 all over x minus -4. By the way, you don't have to go through all this process every single time. After a while, you just start off with that, for example, maybe because you've done it so many times, but it's important that you understand where that comes from. It comes from taking the secant slope and turning it into a tangent slope. Anyways, so this becomes a limit as x goes to -4. This becomes x squared minus -4 times -4. That would be 16 all over x plus 4. You do a little rewrite and you cancel that. X minus 4, x plus 4 all over x plus 4. The part that cancels is this piece. So toward the plug-in method, x is going towards -4. So I got -4 and an end of the -4. I reckon that's -8. Go back to the picture. It should make sense. The slope here. Let me try to draw an actual tangent slope that barely touches it and approximates it with a line as best as possible there. If you were to compute the slope there, we did compute the slope there. It is exactly -8. So go down 8, you go down 1, or you go down 16, you go down right 2. That is the exact tangent slope. We could do this all day long, but let's switch it up a little bit. Okay. Why don't we use our brilliant idea on a different function? Let's switch it up a little bit. Suppose you got x to the third, and you want to find the tangent slope right here at 1. So you're going to find the secant slope as usual. F of x minus f of 1 all over x minus 1. And then you're going to slap a limit. The limit as what? We're going to move the x's closer to 1. Okay? That's going to move my this x closer and closer and closer and closer to 1 to get me the tangent slope, which will eventually be more or less like this. Well, whatever. Okay, talk is cheap. Let's do it. Slapping the limit on both sides. The limit as x goes to 1. The limit as x goes to 1. This turns it into a tangent slope. From a secant slope, you get a tangent slope as you take the limit, and that equals, let me think, limit as x goes to 1. See, this part is different right here. I'm plugging x to the third, so it would be x to the third minus 1 to the third all over x over 1. You try the plug-in method, you get 0 over 0, so that's not going to work. So then you try the little rewrite. The limit as x goes to 1, x minus 1 times x squared plus x plus 1. This is a famous factorization because this is a famous polynomial difference of cubes. And so you get you do a little rewrite here. Then you try the plug-in method. X is going towards 1, so that would be 1 squared plus 1 plus 1. I reckon that's 3. Winner, winner, chicken dinner. See that? So beautiful. We could do this all day long just as long as you have any function. This becomes a limit problem. As long as you can do the limit, you can do the tangent slope. I would do that one, but I'm gonna let you guys do the one at 2. You should do that one for fun. I want to step it up a notch or 2. What if you have some other function such as y is equal to the square root of x? Could you do it? I don't know. See, you would take the limit as x goes to 2, take the limit as x goes to 2, and then you'd get to work. This would be your tangent slope at x equals to 2. By the way, don't you get tired of writing tangent slope at x equals 2? 1,000 years ago, people found out that it gets tiring to write that all the time. Tangent slope at x equals 2, tangent slope at x equals 2. People got so tired of that that they made their own notation for it. They said, you know what, forget about that. We're going to call this something else. We're going to call it f prime at 2. F prime is special notation, which means that the slope of the tangent line at x equals 2. Okay, this means exactly that, but in a much shorter and much more powerful notation. Tangent slope at x, of f of x at x equals 2. F with a little prime, you read it f prime at 2. That equals the limit as x goes to 2 of square root of x minus square root of 2 all over x minus 2. Aha. We've done problems like this before in the section where we did limits. You do the plug-in method, it's not going to work. You need a nice way to do it would be a little rewrite. You could also try engineer's method, but rewrite is especially clean on this one. Square root of x minus the square root of 2. Square root of x plus the square root of 2. I know the bottom doesn't look like a square, but I could see it as a square. It's a square of the square root of x. This is the square of the square root of 2. And in that way I can factor it as difference of squares. Try it. If you FOIL this, you'll get exactly that. Or said differently, you could try the conjugates idea. That's also a famous idea. Either way, this works out nicely, and so you get let's see, what do you get? Now I'm going to try the plug-in method. X goes to 2, so that would be the square. I get 1 on the top, by the way. Square root of 2 plus the square root of 2, that would give you 1 over 2 square roots of 2. See why they pay me? Tangent slopes. We're going to have a tangent slope party now. For homework. Oh, you're going to have a tangent slope party. Let you do. Oh no, we didn't. Ooh, I wish I hadn't done that. Look at that. Does that scare you? Haha. Does that scare you? An ln function. Yeah, let's take it up a notch or two. All those other examples were pretty easy. Probably your previous high school teacher did them for you. Or your tutor, or your PE coach, or your friend who's good at math, or your boyfriend or your girlfriend who's took calculus. They can do all those. Let's do something they can't do. Let's do it for an ln function, ln of x. We're going to find the tangent slope at x equals 5. Yeah. In fact, I've never done this before. If you want to take a little break, coffee break, go ahead, come back and bring your game face on. We're going to need a couple ingredients here. One of the ingredients will be this idea of flipping a fraction. If you have 1 over b and 1 over a, you could flip it and get a over b. But you could also do it backwards. If you have a over b, you could rewrite it as what it was before it got flipped. Right? These two statements mean the same thing, but they suggest different things if you read them from right to left as opposed to left to right. Anyways, that's algebra. It's famous. And of course, from the limit section, we had this incredibly famous limit, 1 plus a constant over t raised to the t as t goes to infinity. If you remember, that's equal to e to the k. Super famous. If you don't remember, you got to go back and do that homework. These are the key ingredients, and we will do a little bit something that's not so trivial, something a little bit more interesting than what you might have seen before. It's a little bit more interesting than what I've seen before. So I'm gonna pause this and then do it. I should probably say that, summarize what we've learned today. Today we did one of the most important things that we'll do all for a long time. We defined the tangent slope. When this slope exists, which it doesn't always, I'll have some examples of that in the homework. We denote it this way, f prime with a little c. And that, whenever you see that, you should know that's the slope. That's the tangent slope. Tangent slope of the graph of f of x at x equals c. And the most important thing, one of the most important things we did today is define it. This is the limit as x goes to c of f of x minus f of c. all over x minus c. That right there, that's the most important idea. And not only that, but you shouldn't just memorize this. You should know where it came from. And the second most important idea is where it came from. It came from taking the secant slope, which was just f of x minus f of c all over x minus c. And out of the secant slope, we make a tangent slope by slapping a limit on both sides. That right there is the most important thing. And with this, you should be able to go on the homework and do this all night long. You're going to have a tangent slope party. I'm going to give you like 1,000 problems to do, where I simply ask you, I give you a function like the ones we did today, x squared or x to the third, and I tell you at 5, give me the tangent slope, at 7, give me the tangent slope, at -3, give me the tangent slope, and you're going to have all kinds of fun finding all sorts of tangent slopes all day long. That's the most important thing we did today, and that's the most important thing we'll do for a long time. There's still a lot of other things to do. We got to define, there's a second definition of this, a second way of looking at it, that is sort of famous, so I want to take a look at it, and I might post that on the homework or the next section, and then there's a lot more ideas that we have to develop. Anyways, if you're short of time, or if you're beginning, depending on how you feel, you could just stop the tape here and go on and do the homework. But if you've got big dreams and big ambitions, I suggest you stick around here and watch the rest of it, because we're gonna get crazy here. We're gonna do the derivative. We're gonna find the tangent slope of this function ln x, something that you don't see every day. Okay, and this is, so I guess you could say this is optional. If you have the inclination, you should stick around. Otherwise, this is, if you got this, then we'll call it a good day. Okay, so it's option for. I've never done this, but you know, I started taking Pilates class and body pump class, and they always tell you, oh, there's an option. If you want to do the push-ups, the real push-ups, you do them your whole body, and they always give you an option. Or if you're, if you're weak, like me, you put your knees down and then you do like baby push-ups. I never thought about that, but now I'm thinking about it here in math class. Or like Pilates class, they always give you 2 positions, one for the real pros and one for the beginners. So now I'm gonna start doing that too. Option. You guys can stop here. For the rest of you, let's get crazy. Alright, so this would be equal to the limit as x goes to 5 of ln of x minus ln of 5 all over x minus 5. And it's still just, at the end of the day, it's still just a limit question. Nothing to be afraid of. We still have our famous 4 methods: plug-in method, engineer's method, rewrite, graphing method. So at the end of the day, it's not that bad. And 99% of the time, if you do the engineer's method, we will get there. We will get the, in fact, you could pause it here, do the engineer's method, you'll see that this limit is 1/5. Okay? But the engineer's method is alright when you're a beginner. That's option. For the rest of us, we want something a little tighter, and so I think it'd be instructive to go the extra step here and do it. So this would be the limit. I'm going to try a little rewrite on this one. Rewrite. X goes to 5. The difference of logs would be the log of the quotient all over x minus 5, right? And of course that would be equal to the limit as x goes to 5 of 1 over x minus 5 times the ln of x over 5, right? So all I did is take this and put it as a coefficient in front of the ln. And I do that because it suggests the following property. If you remember, every time you've got the ln, if you have x here, ln of a, you could take this x and put it up here as a coefficient, and it becomes ln of a to the x, right? You remember. So I'm going to do exactly that. I'm going to take this guy and put it up here. And that will become, I'm going to need another page for that, that will become the limit as x goes to 5 of ln of x over 5 raised to the 1 over x minus 5, right? Well, can you see that? Let me see if you can see that. Where's my scroll? Yeah, you can see that. That's good enough. Well, no, you can only see that. There. Alright, so then I'm not done. I'm just getting started. Then I'm going to do this amazing trick here, a famous trick actually. I've seen it done many times, and if you haven't seen it done many times, well, get used to it, you will. Here it is. I see this x minus 5 figure here and I see only x here, and I wonder what would happen if I do x. I wonder what would happen if I do x here and then I do -5 and +5 and leave everything else the same. Leave everything else the same. The reason I do it is because I want to see that x minus 5 shape here. That would become the limit as x goes to 5 of ln of what would it be? X minus 5 all over 5 plus 5 over 5. I'm splitting it because I'm going to get 1 here, and that will give me limit as x goes to 5 of ln. I'm going to switch the 1 over here, so it'll be 1 plus x minus 5 over 5 raised to the 1 over x minus 5. And slowly, you know where I'm going with this. I'm going towards this famous limit here, the limit of 1 plus k over t raised to the t as t goes to infinity is equal to e to the k. I'm going to try to use this famous idea to try to simplify the problem at hand. This is the problem at hand. This is what I'm going to try to use to simplify it. So I keep on going. Oh yeah, this is where I use the other fact. Remember here, I could take any fraction I want, a over b, and I can rewrite it in this funky way. Right? This is just algebra. So I could do that, for example, if I have x over 5 all over 5, I could rewrite that as 1 over 5 all over 1 over x minus 5. Because if I flipped it over, I would get exactly the same thing. This is nothing fancy other than just algebra and some creativity. By the way, that's what we sell: perfection, beauty, and creativity in reasoning like you've never seen. That's what mathematicians sell. We don't sell cars. We don't sell coffee like Starbucks. We sell perfection, beauty, and creativity in reasoning like you've never seen. Here it is. This is creative. You flip it the other way, sort of unsimplifying it. Why? Watch. By the way, when I was your age, nobody showed me this stuff, man. I had to think about it, lose sleep. 5 wives later. Here it is. 1 over 5 all over 1 over x minus 5 all over 1 over x minus 5. And to what end? Well, here's another crucial piece of information. As x goes to 5, let's just, for the sake of it right now, let's pretend it's coming to 5 from the positive side, okay? You can deal with the negative side later, but let's say it's coming from the, I'll put a little dot there. It's not exactly equal, but we'll deal with this later. If x is coming to 5 from the positive side, this is becoming a little bit more than 5. And when you subtract 5 from it, this becomes a really, really small positive number. 1 divided by a small positive number becomes a huge, 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 huge number. That, my friends, that's going huge. This is going towards infinity. This 1 over x minus 5 is going towards infinity as x goes to 5. So this is also going towards infinity. This is exactly the same number. For the same reason, you got 1 divided by an incredibly small positive number. What that means is that I could rearrange this, and I could say this is equal to the limit of ln of 1 plus 1/5 all over something. And here's the thing, x, or I'm going to make the substitution here, t. I'm going to say t goes to infinity, and I'm going to replace it with t and raised to the t. I don't know if you can see that. Can you see that? Man, I wanted this to be super perfect. T, right? Because this portion is going towards infinity, this portion is going to infinity, this portion is going to 5, so I change everything. As t goes to infinity, this will just be, I can replace this with t, and that goes with the t. All these quantities, as x goes to 5, these ones are going towards infinity, so I can make the switch, t goes to infinity, and switch these to infinity. What that does for you is it gives you, oh, but wait, there's more. Also, can you take this limit and take it in there through the ln function? Yes or no? And of course the answer is yes, you can. You could take it through the limit as t goes towards infinity of 1 plus 1/5 over t raised to the t. The reason you could take this limit through the ln function is because ln is a continuous function. This was one of the big ideas. Remember when we did continuous functions, we had 4 huge ideas. One of them was that you could take the limit through there if this function is continuous at this point. Well, what point is that? Well, this is a famous limit, this is limit looks exactly like this. So this limit is equal to e to the 1/5. And the question is ln, the log function, continuous at that point? Yes, it is, so it was okay to take the limit through there. But wait, there's more. This 1/5 can come out here, and you have ln of e. Well, how much is ln of e? Well, that would be just 1. And now you see why they pay me insane amounts of money. I have one word to say about that. Yippee-ki-yay. No, 3 words. Look at that. So beautiful. Take the limit. Fearless trick right here. Creative. Move it around. Fearless. Not afraid. Make the switch. This thing is going towards infinity. Fearless. Math algebra skills. Famous limit. 1/5. Yippee-ki-yay. Alright, so I think that should do it for today. The homework will be super important. It's not up yet. It's being cooked up as we speak. But probably by the time you watch this, it'll be ready. The homework will be super important. You gotta be very good at finding tangent slopes. That's the name of the game today. And do me a favor, right? Every time you find a tangent slope, can you please say it out loud? Yippee-ki-yay. And we'll see you guys here next time. Okay?